I would like to thank the organizers for the very kind reception and your great hospitality. It has been very beautiful, everything. I appreciate it. Well, I graduated as a student at Burns in 1997. Well, it's clear that for me that Dan Burns is a very special person and with deep knowledge of mathematics and very wise person. And I remember, for example, when I was ready to finish up my dissertation, I had some family crisis and I didn't know whether to go back home or not, and he just gave me a few sentences and then it clicked, and I went back home and came back, and it would have been so bad if I hadn't. And then so I'm so thankful that he just said the right words. So you got to be there, basically. But so I'm really grateful for that. And also, well, grateful because the subject of the Grauert tubes were mostly pioneered, but done in a way. Well, I know he's making faces, but but in a way you can track it. Not necessarily. Let me explain what I'm going to say. So I'll get to that point. So let me review the setup. Some overlap with what Sujay said. Let's start with MG, real analytic. Riemannian manifold. And well, there is an open set that exists. There is always an open set in the tangent bundle. Let me call the open set U in the tangent bundle that contains M as the zero section. And in it there is an adapted complex structure with an adapted I'm not going to go into the history of precisely how that started, but I'm going to say a few things when I at some point. The adapted complex structure, this structure is defined as we already heard, but I will have to be a little more precise. Is defined by requiring that along that for every geodesic in M, the map, well, we can keep that notation. This is a map in C, from C to the tangent bundle, and we have parametrization. It is holomorphic. Now I have to be careful with where this map is defined, because it will be crucial for what I want to say. So that we're defined, okay? Because in general this map will not be defined for the entire complex plane. That will have to be with well, related with the radius, but we're defined when defined. Well, it's holomorphic. Well, probably we can. Well, let's say well defined is the holomorphic part will tell you where it stops to being defined, because at that point it wouldn't be a complex structure. So we're defined in that sense. It's always defined as it is, but not as in a way that you can define holomorphic. But so we're defined. I don't want to be. We're defined. Okay. Now, as you can imagine, this open set, unless There's a lot of symmetry. In principle, you know what it's going to look like, but you can concentrate on special subsets, and those are where the Grauert tubes. Grauert tube is a set of the form TRM. I'm going to use capital R because my little r looks like an N, so it will be confusing. I'm going to use capital R for the radius. And provided that it's in U. U is that open set. The open set. Okay. With the adapted structure. Less than. Thank you. Thank you. So provided that that fits into the open set, then that's what I'm going to call a Grauert tube. Okay. Well, there are a couple of things I would like to say. One is that that radius might not exist if the manifold is not compact. For example, you might have too much negative curvature that will come up in one of the inequalities. That's already known. But if it's compact, then you always have a radius. So let me put complete, just to make sure that there are no problems. Okay, so this Grauert tube, or even this one, has a complex structure, and because it's a subset of the tangent bundle, then it has a symplectic structure. So it has a complex structure. A symplectic structure. And the manifold M sits as a totally real submanifold. So this is something that even if the function M happens to be already a complex manifold, then still that complex structure in M is ignored, at least for the definition of the Grauert tube. So all we have is a totally real submanifold sitting inside the tube. And with this addition that we have this function, which is the energy function. It's called this energy square. The energy function. And well, you have the symplectic structure coming from the tangent bundle. You have so theta is the symplectic structure. Where theta, well, you define it as with the projection. Where pi is the projection in the tangent bundle. And the complex structure, of course, is the adapted structure. And it has the center, which is M, the thing we started with, so it has the center. Okay, so that's the setup. So these two things then are the form a Keller manifold. And in a way, this is sort of like a canonical extension of the Riemannian metric, this Keller structure. Now, this is what I prepared as a joke. This is a conference in complex geometry, symplectic geometry. So I'm going to talk about the Riemannian part. In the following sense, as a complex structure, this is supposed to model certain complex manifolds with functions that satisfy the Monch-Ampere equation. So that's where things, in a way, started in my, this is the literature that I saw, with the classification of Cn by Dan Burns, where in that case you have a Kähler manifold with a particular function with properties such as satisfying a Monch-Ampere equation, homogeneous, complex Monch-Ampere equation. And in that case, you don't have an M as a center, but you would have a point. So Cn can be classified using some Kähler structure with a particular extraction function. And you can use that to classify or characterize Cn. If you look at the same kind of problem, but now allow the center to be a totally real submanifold, then you have this kind of situation where you can model that complex manifold with a structure like this. So this serves as a model for studying that kind of manifolds, where you have a totally real submanifold and you have the function that satisfies the Monch-Ampere equation. I'm not going to use that, so I'm not going to write that down. What I'm going to concentrate on, as I said, is in the Riemannian structure and how that Riemannian structure is related to, for example, how far you can go with the radius. That's my emphasis. So in other words, can you tell from the metric how far you can go on what kind of conditions you have to impose? One of the conditions that motivated looking into this is inequality by Lempert and Zöcker. This construction of the essentially the same construction of the adaptive structure in the tangent bundle was done previously for particular manifolds by Patricio and Wang, I think, for symmetric spaces. Then that construction was generalized for arbitrary manifolds by Gilman, Stenzel in the cotangent bundle, and by Lempert and Zöcker in the tangent bundle. Now, for the kind of thing that I'm going to do, the construction of Lempert and Zöcker is very explicit, and that's the one I'm going to use extensively. Okay? The other one, by Stenzel and Gilman, is more towards the looking at the Kähler structure and the Monch-Ampere equation. So I have to review briefly the construction in a moment. The condition, let me write down the following then. My question is, how does the metric determines the radius? Now we also heard that looking at Grauert tube, but what Sachin said today, looking at the radius is not the most general thing you can. Looking at a disk is not the most general thing you have to do all the time. For example, it's not even clear that this complexification is the best that you want to have for whatever reason you want to do something with a complexification. So in other cases, there are other complexifications that don't take into account the metric but a connection. Okay, in this case, you have a connection which is the Levi-Dirichlet connection. So you can do that, and then with that connection, or you can use another connection and have a complexification as well. The definition is more or less similar, but I want to go into just the Riemannian case. So the question is, how does the Riemannian metric determines the radius and the maximum radius or radius, the existence of a radius? And the prototype of that is an inequality by, as I mentioned, by Lempert and Zöcker. So when they described their construction, one of the theorems that they ended up the paper with was, maybe there was something extra after that, but I think that that's basically how they ended, was an inequality that is more or less following. So a Grauert tube, I'm paraphrasing just more or less, essentially this is what it says. A Grauert tube of radius r exists if For that situation, real same mg, then the sectional curvatures, then sigma, the sigma sectional curvatures. Okay, and P are equal to. The equality is interesting because it's the constant curvature case. If there is a discrepancy with the radius, well, it's because I defined the radius in that way. You can use some 1/2 somewhere, and you will get a discrepancy. But I'm using that definition of the radius. And this is the inequality that you get, or they get. So that means, in particular, that if the radius is infinity, if you want the complex structure extended to the whole tangent bundle, then you need non-negative curvature. That's for the sectional curvatures. Zerke proved simultaneously, well, in the dissertation, his dissertation, he proved next order inequality, where now he considered the case of 2 dimensions, in which case this is just the Gauss curvature. And he has an interesting inequality. When I saw that, I thought, well, there is something really neat about this inequality, and it stuck to my mind. And I decided to just look into it relatively recently. And it's really nice, I think. Well, Zerke proved in his dissertation I'm going to call that Zerke inequality. Dimension 2, sigma now is the Gauss curvature. And he proved that. Okay. Oh, this is a Laplacian. Oh, no. For the case R infinity, so let me write that down. So if the Grauert tube exists with radius infinity, I think I might. Then you have this.
So is there a quantitative right-hand side like -4 pi?
Here, no. This is what he proved as an inequality big equal to 0. It's just a computation of a derivative of a function, which I'll explain where it comes from. I will get to hopefully to a point where I can point out where this comes from and what I did to get the whole set of inequalities. In particular, I will get an inequality that is for any radius and stronger than this one. So this is the kind of inequalities that I would like to, I wanted to push a little bit harder to see whether this will tell us anything about how far you can go with the radius. So it was natural then to consider curvature inequalities. Of all the entities that you can use in a Riemannian metric, for example, the curvature is one of them. And it seemed wise to start with 2 dimensions. I'm not wise, but I started with 2 dimensions anyway. So so the question now is, let me refine the question then. How does the Gauss curvature, I'm going to refine and make it more narrow. How does the Gauss curvature, by taking a 2-dimensional case, determines the radius, or how is it related with the radius? Okay, and looking at the problem of the construction, the hint basically is, if you want to call it that way, is hint that when you look at the idea of why you're going to end up looking at this this particular kind of function is, the hint is that you're going to look at, you consider that, let's f of t be the geodesic flow. Extend it to Tm or even Um, it wouldn't be, you can always extend it to geodesic flow. Okay. And when you look at the differential of the geodesic flow, let's say, the differential of the geodesic flow, then you get the Jacobi fields. The Jacobi fields are in 2 dimensions. They are easy to write down because you don't need matrices. So in 2 dimensions, the Jacobi fields are the things that are taught in first course in differential geometry, random geometry, and you have an equation, Jacobi fields. The equation will be basically equation, say for normal Jacobi fields, which means that you're going to look at vector fields that are perpendicular to the velocity. So these are Jacobi fields. Equation for normal Jacobi fields. And that equation is just an equation of the form f double prime of t plus sigma of t equal to 0. T. That's the equation. So the extension to a given radius and or to the entire tube. Yes.
What is UM?
Pardon me?
What is UM?
Oh, the unit tangent bundle. I'm sorry. Actually, I don't need to restrict the unit tangent bundle if I extended it properly. Could be but that was the unit tangent bundle. I'm going to write it anyway because I will probably write it again at some point. Unit tangent bundle. Thank you. And that's the tangent bundle. Let's put it that way. You can extend it. The tangent bundle. And the tangent bundle as well. It does make a difference at that point because you're looking at the tangent space. But anyway. So this is the Jacobi equation, Jacobi field equation. Okay? And what you need to look for in order to determine whether the complex structure extends to a radius or not is this. You need to take quotients of Jacobi fields along every geodesic. And if those quotients extend in a particular kind of way, what I'm going to write down in a second, then the tube extends to that radius. So in other words, you consider, so the radius of the Grauert tube. The Grauert tube extends to radius r if and only if for every geodesic the quotient of any two independent, well, dependent as well, but independent Jacobi fields extend as follows. Any quotient extends as follows. Okay. Say H F2 over F1. So H is analytic in the upper half plane, and with non-negative imaginary part there. Excuse me, this is for R infinity. Okay, then I have to revise that for R equals finite. But and for R finite, the reason I do that is because this class of function is well known. The other one is also known, but it doesn't have a name somewhere. And for R infinity, for R finite, H extend as analytic. With extends analytically with positive imaginary part on L0. So in one case you have the whole upper plane, the other case you have a strip, radius, the height is r. Now this function, the quotient is analytic, real analytic, and the only problem that this quotient has is at the zeros of the Jacobi fields. So automatically this thing will be defined, h in both cases will be defined, will have to be defined everywhere except at the zeros of the Jacobi fields. Now, this is a second order equation, so the zeros are simple and they will be obviously real. And what you're asking is that there are no more zeros and no more poles. The poles are the zeros of this one and the zeros, obviously. And the reason is that these two are independent, so they don't have common zeros. Okay? So that means that automatically you have this defined, and by reflection you automatically get the lower half. So you're going to have this extended in the whole plane with poles that are real and zeros that are simple, real poles and zeros. Everywhere the action happening essentially in a discrete set of the real line. In this situation you have the same. You want the same, the poles. You have a function. But now you stop at some point. So you have the. So in other words, you want a meromorphic extension with zeros and poles all along the real line and simple, all of them. Now those, of course, are for a particular choice of these two functions. You're going to have that the zeros are well. Has to do with conjugate points. You define conjugate points that way. But there is no canonical, there's no reason why you should pick one over the other. So there is a relation, though, between different choices of solutions, and that's a Moebius transformation with real coefficients. So the fact that this extension exists will be preserved at that. So what you're looking for is something that inherently is invariant by the Moebius transformation. And that's where the curvature comes in, obviously, because this is related to the Schwarzian. Okay? So it seems natural to look conditions that can be expressible in Schwarzians. And because these are higher order conditions that you are looking for, well, you need to think about what the higher Schwarzians would be. And, well, in retrospect, of course, you're going to get infinitely many conditions because this is a real analytic problem. So that's what you get. But that was essentially already used in this, but not with the full force of the problem, and I'm going to explain what that means. So to get the inequality that I just erased here with the rate, well, actually this one, Lemper and Soke looked into this one first, this kind of function, and then they map it into this strip, then a chain rule, and give you the curvature condition that I erased. The one that I erased even later, I just, oops, this one, I always do this. This one is also obtained using properties of the derivatives of functions that extend in this way. Now, these functions are called Pick functions, or Nevanlina functions, or Herjolf's functions. That's the names that I found. They're known for many, many years, so it's very classical. I'm going to use pick functions because it's shorter. And in some literature, that's what you always find. In another literature, you use only Herglotz, another Levellina. It depends on what the framework is normally. Actually, I learned this as a pick function. I don't remember what Lempertz used, what nomenclature they use. I don't know. I remember. And so let me quickly review what the Schwarzians are. So let's begin the higher order Schwarzians. So I'm going to pause. Higher Schwarzians, fine. I said that there was no preferred quotient of solution. I'm going to look at a quotient of two solutions of the differential equation. Okay. Now this could be a differential equation along the real line, but then it will be transported, which is already hinted here at, to the tangent bundle by a little bit of a correspondence that I have to explain. The higher Schwarzians is, well, you start with now the higher order Schwarzians will be associated to the differential equation. Okay, so you start with h. So suppose you have an x. Now normally the Schwarzians are computed with functions that are analytic, but this has to be just infinity because it's just a generating function that I'm going to write. So x is a real number, and you take h, a quotient of two solutions. It doesn't have to be a quotient, but to shorten it, I'm going to just stick to the fact that you have two solutions there. That's what I will be thinking of. Okay, a function of t of. And I'm going to write an expression in terms of a generating function. And normally, to get the first Schwarzian, you're looking for a Moebius transformation that will take your function to a particular form with value 0 at 0, or at the point you're at 0, second derivative and first derivative equal 1. The next term in the Taylor series or Maclaurin, whatever your point is, will be the Schwarzian. That twice the twice the that curvature times 2, I think. I need to think. So you start with we start with the function, assuming that this is different from 0. Then you can take care of the 0 value at 0. So when t equals 0, this is 0, and then you have a Moebius transformation. I'm going to write it down so you have a sense of what how the variables change, because there are two variables here, and I want to make sure that doesn't get lost. And so that's an expression in x and t, and you want that's a generating function. From 0 to infinity. So those are the higher order Schwarzians. I'm going to write as the sigma because it depends on the curvature. So the higher order Schwarzians. Okay, so let me just write down a few. The first one will go easy. That's the that's the classical Schwarzian. And there is a recurrence for the other ones, but they are all coming from this generating function. So let me write down one more. It's just a derivative of this one. So if I get this, it's just a derivative of that one. So it's just in this particular case. And there is a recurrence that is not just a derivative. There's other things going on, but I don't need it. So I'm gonna, pardon me? Oh, this is a generating function for the Schwarzians. This is one way you can generate a function. what I said before, maybe when you define this Schwarzian, one way to do that, to define that one, is to take the function you're computing the Schwarzian of, and then normalize it so that the coefficients of the Taylor series are these ones. I got a 0 here, sorry. 0 there. That's a 0. And the next one that is not, this is the Schwarzian. And it ties with the differential equation because this is 2 times sigma in the differential equation. That's well known, the differential equations, that elementary differential equations, 2 sigma. And that's the Moebius transformation that will do the normalization. The reason I write it this way is because you can see that it depends on 2 variables, just like the generating function. So if you want to change what the value of the higher Schwarzian is at x, you need to change the x here. And the Taylor series for that will give you still the right Schwarzian at the different points. So that change is not a constant. It's a function of x, and it varies according to this. Now, it's easy to prove that this is invariant by Moebius transformation because you're normalizing by a Moebius transformation anyway. So in case this is not happening, you can take 1 over that. And because of the series of the Jacobi solutions, then you get it right. Either that or 1 over that will not be 0. All right, so that's a classical Schwarzian. And these are the higher order Schwarzians. Okay, so let me define, just to keep it short, as short as I can. Let me indicate one thing at this point. Maybe with that already we can characterize the existence of a Grauert tube of radius infinity. One, and the reason is that, well, let me, for R infinity, maybe, this is like a little theorem, but I don't know if I can get theorem 1. The Grauert tube of radius infinity exist if and only if the following inequalities I will have to are satisfied. And what I'm going to do is to write down a determinant of a matrix, which is a Hankel matrix. A Hankel matrix is a matrix that has not these diagonals with the same entries, but with these entries like this. So I'm going to put the first Schwarzian here, then over 1 factorial. So these are the Taylor coefficients. Those things depend on x. So I'm going to put this. I think if I can do it big enough so that the pattern is simple, but I can make it not look simple if I mess it up too much. So x, I will drop, well, maybe I put the sigma. So we have this pattern where you have a dependence that will be clear when I write the formula, etc. You continue that way. So in other words, you're going to do the determinant of a matrix. I'm going to write down the entry as I plus j minus 1 factorial. That is an entry that depends on I plus j. That means it's a Hankel matrix. And of course, this is saying that there is a quadratic form of a special kind that is non-negative once I put this for all n. For all n and all x. So these are inequalities. Again, that determinantal inequalities. The first one is trivial because there is a 1 there. the second one, that is to say the 2 by 2, will give you the Lampert circuit. And the third one will give you a stronger version of circuit inequality, because in what they showed in their paper, what they used was properties of derivatives of those functions, which amounts to looking at these Schwarzians. But they looked at the diagonal part, not the quadratic form. But if you look at the positivity of the quadratic form, you have a stronger condition, obviously. And that stronger condition is what you need in second order and higher to get the condition back. Now, I thought I was going to be able to write down the thing for the radius, finite radius. But maybe I can in 5 minutes. I'll give an idea. So for radius r, I have that till 420, right? 20, okay, thank you. For r finite, I'm going to write it directly because no motivation. So I'm going to write down, I cannot give the, I'm going to write down sigma. I'm going to keep track of the curvature, and I'm going to keep track of a map. JR is a map. Probably I won't be able to give the motivation. I'll just write one example of the map. So you can take any map. For example, you can take JR to be minus r over pi log 1 minus pi over r z. And you take the argument so that this is mapped, is a map from the complex plane with a cut into the strip. So this is a map that, so you take a cut. Now the reason I picked this one over that one with a plus is because the derivatives have all positive sign, and I don't have the luxury to drop to C2 coefficients. So this way you can get rid of the trouble of dealing with signs if you take this one when you take all the. And anyway, so there's a cut that looks like this, but the point is that this is free or analytic, and this function has positive imaginary part on the upper half plane, lower on the lower half plane. So this is a nice function to compose with a quotient of solutions, and that's what you do. So you take a point, this is a point 0, then you're going to map this to x by taking a translation. Tx is translation, and then you're going to compose with the function, with a function h x. I'm going to say what that is in a second. So rather than writing a generated function, I'm going to give you another way to define this. So I'm going to define, this is a shortcut definition, say JR Schwarzians at x. So let's take h of x to be the quotient of two particular solutions, the ones that you get by putting the initial conditions that are special for the point that you choose. If you take one, put a 1, this one, I want that to be 1, that's right, and then the other one, you want the other way around to be 0. I think I want that to be 0. I want that to be 0, and that not to be 0, right? That's right. Okay. So these are two particular solutions that are called the fundamental pair of solutions. And then you take the function f of x. You take this function, h. I'll write it here because it's quite important for understanding this. So you take that function. I would like to say something about the details of the presentation because that's the interesting part. But so you take f of x. You take the composition of the two to take the JR map, and then you take the derivatives of 0, and that is by definition the Schwarzian. If you want, you can use this as the definition of the new Schwarzians, where now you get a deformation of the original ones, because when r goes to infinity, this goes to the identity. So the equalities that you get are going to be essentially the same. It will be the same equalities, but now depending on the parameter r. When r. Oh, these are solutions. Excuse me. Solutions of. Sorry. So two solutions, and you put initial conditions. You have a point x. You want to define a function. Okay, I want to define a function, and I want to define pointwise. Other than I could have done it with the generating function, but it's equivalent. This is shorter. X is the point that you pick. You solve the equation, find a Bayes transformation with the two solutions, make this up, these two, make this construct these two solutions, and then take the quotient. No, this is an x. You mean these two? These are the same x's. Is that what it is?
Same.
Yeah, that's the same. X is a label for the function, and then I put initial conditions. What's the initial condition? Well, when the t coincides with the label x, that has to be 1, and so forth with the other ones. Is that two labels? This is a label for the function. That's the variable when evaluated at x equals x. That's right. These are all of t. That's right. That's right. That's why I put all the variables here rather than make it implicit. I want to be explicit there because for that reason. And maybe this I should have written. Maybe that's what I was missing there. T. All right. So so you take the derivatives at 0, and you get functions that are deformations of the original Schwarzians. And the condition, so the theorem is now theorem that the Grauert tube of radius r exists if and only if, well, for all n excuse me, well, I jumped to the well, if only for n and all, I have to say something, and all v in um, say, for example, you get a determinant of I plus j minus 1 sigma jr I plus j minus 1 bigger or equal to 0 for n, and I have to put a twiddle because the twiddle is not this function still. I need to introduce something else, and so I need to tell you how to transport those functions into the tangent bundle, because the way I define it here, I took two solutions of two differential equations on the real line. The statement I wrote to cut it to fit it in is about the Grauert tube, so I have to be a little bit more careful. So there's one more piece that is missing. I'm going to try to connect it now. Is the following: where are these functions? So where are I'll put a tilde. These are functions on the tangent bundle that are real, that reduce to these functions along the unit, along a geodesic. And the way to write these functions is as follows. So to write down the functions, to write down the Sn on Tm, well, we use the so-called Tamanoy polynomials, which are, say, Pn. They are not exactly. There is a 2, so I'm not being entirely. There's a 2 missing, but I'm going to call that the Tamanoy polynomials. Up to a 2 times the variable is the Tamanoy polynomials, where he discusses the higher order Schwarzians and expresses them as a polynomial in the curvature and covariant derivatives. So you can write Sn at x as a polynomial in sigma, sigma prime, sigma n minus 3. And this Schwarzians, the Schwarzians that you get by this computation will simply be linear combinations of this with coefficients that depend only on R. So from this you get that the higher Schwarzians with the GR attached to it. So we have the I haven't put the tilde yet because I'll put it in a second. This is a polynomial in sigma n minus 3 derivatives and pi over r n minus 1. So explicitly, I guess you can just even write it down. The summation these are the Stirling numbers of the second kind for that particular choice of JR. So this is the coefficient of n of k of n to the k of n plus 1 n time n plus 2 times etc. up to n plus k minus 1. It's a racing factorial, one of the kind. But it's something you can compute. It's easy to compute. I have it's easy to compute. But these are just numbers, constants. Okay, and for the tilde then, we can get the functions by simply changing the covariant derivatives everywhere you see them. By taking the derivatives with respect to t into covariant derivatives with respect to the vector you are at. So let me write down the formula. But there's one more thing that you need to do. So for S in the tangent bundle and sigma r Gauss curvature, you're going to have to add a couple of things here. The quickest way is just write it down. You get so that's V in the tangent bundle. Now, along the zero section, this becomes trivial. The only one that survives is the first one, but on the other ones are not pi. And these ones are tilde of n sigma of v. And these ones are not the ones that you get putting this, replacing that by covariant derivative, but by the following. So you're going to put Sn sigma v, you would take Pn, you're going to put you're going to multiply every time the function by the square of the length of the vector with respect to the Riemannian metric, etc. And the reason to do that is because the curvature, if you view it as an obstruction to integrability of the distribution that you get with the connection, that obstruction varies with the square times the curvature that you get in the base. So for that reason, yeah, you have a question? Oh, no, sorry. All right, so this is the way you construct the functions. And let me indicate why the inequalities are true and what theorems are behind that. So the claim is that if those inequalities, so the theorem, let me write it here. So Grauert tube radius r exists if and only if, again, the determinant of S I plus j minus 1, I plus j minus 1 factorial. Well, put the jr at v is bigger or equal to 0 for all n. Okay, and all v in Tm. In UM or in any, this can be made smaller, but it doesn't matter. I want to say a few words about one direction and the other direction. In one direction, the necessary condition can be derived in many ways. Classically, this is a theorem by Lohner theorem. This is a Lohner theorem, essentially, what this is. The way I think he proved the necessary condition is, it doesn't use this. I use this because this is what I was using working on this setup, which is the Fatou representation for functions that extend analytically as peak function. How about that? That's why I put peak functions, of peak functions. So you have a function that's a peak function like fx, like that, and you have a representation. Now I'm going to put the label x because these are going to be numbers that vary with x, and then you're going to take an integral, and then you're going to take well, there's a Borel measure. It's a Borel measure that you get. Now this is classical, and this is Poisson representation pulled back to the translated to the upper plane, and this is the mass at infinity that you get. And well, I don't have I have 2 minutes. You can take derivative under the integral sign because the measure has no mass at 0. Okay, now that's all I can say. But there is a nice trick to get the inequalities for the determinants, which is you have to recognize that you can reconstruct the square of a determinant, which is a nice computation, but unfortunately I ran out of time. I have 2 minutes. I won't be able to do that one, but it's really neat. And then, so there is, in this determinant, you can rewrite it essentially as moments of negative powers of t. Now, the converse is the deeper part, well, deeper one, if you don't take this into account, in the sense that you need something extra. The other part, that is to say, when you have this inequality satisfied and you want to show that the function extends, uses the Hamburger-Mommer problem in an essential way, at least in the way I know how to do that. So therefore, in this direction, use the Hamburger-Mommer problem. That's why, in other words, you can, if the functions satisfy those conditions, then this is a sequence, a Hamburger sequence. That means that you have a measure, another measure, it's a different one, and you can actually write Sn as a power. It's a measure, well, a negative measure. It has to be a positive measure. All right, so in that case, what you're going to get is a function extended, not represented as a Fatou in the Fatou way, but in a Hilbert type of function representation. So you're going to get something, I don't have time for the details, but you're going to get something like this. And I'm done in a second. And it's going to be actually not between infinity and minus infinity, but between 1 over rho and and minus 1 over rho. So rather than getting something like this, with this measure you're going to get something like this. Now the point is that the mass has bounded support, so you can interchange the summations with integrals, and you get this in this kind of expression. So this is labeled by x because this happens for every x. With that, you can reconstruct the function that extends to the strip. The computations are really nice. This one again uses the fact that the measure is bounded, or the support is bounded rather, and that comes from the fact that you have this condition. It can be, there's a radius of convergence that you need to take into account for that to limit the support that you know is limited. And I think the time is up.